right. So we have one more topic before we finish up. And that is statically indeterminate problems. And because it takes too long to write statically indeterminate all the time, I can write SI problem for statically indeterminate. So when is a problem statically indeterminate? Let me give you an example of a statically indeterminate problem. Let's say that I have a wall. I have my good old friend bar with changing cross-section, like that. And let's say that I applied a force right where the section changes. Let's say that this is section B. This section here is section C. Let's say that this section here is section D, so that I can call this force FD. And let's say that this area is, this little area here, let's say that this little area here is A0, and say that this big area here is 2 times A0. And let's say that the bar is made of a material with modulus E. And all this stuff is known, and let's say also that the bar, these 2 sections have both, each of the 2 sections have a length L. So the whole bar has a length to L. That looks totally doable to me. Well, here's where the new wrench comes in. It comes in because I tell you there is not just one wall holding this thing up, there are 2 walls holding this thing up. I have a bar that is built in at both ends with walls on both sides, and I'm applying a load at the middle of the bar. Okay, so I'm given A0, E, L. I'm given the force FD. And what I want is the displacement at L, in the middle of the bar. The displacement at the section D. If you want, you can call this one UX at D. Well, I can tell you we're going to hit a roadblock right away, because as I start from doing my free body diagram of this bar, let's do a free body diagram of this bar. And I have my FD right here. On this end, I had a wall. The wall is giving me a reaction. Let's put Rx at B. On this other side, I had another wall. Okay, so this wall is also giving me a reaction. Rx at C. When I do the sum of the forces x equal to 0, I get Rx at B plus the force that I'm applying at D plus Rx at C equal to 0. I have one equation, and I have 2 unknowns. So I am extremely unhappy because I cannot solve this. I cannot just use equilibrium to solve this problem in my normal forward way. So that's why it's called statically indeterminate, because just equilibrium alone, static equilibrium alone, cannot determine the solution. There is something else going on. This is like, say that you live alone. There are dishes in the sink. You gotta do those dishes. There is no indeterminacy. You are the only one that can do the dishes. If you got one single wall, that's the wall that's gonna hold things up. Now, if you have a roommate, and there are dishes in the sink, it's not quite clear who's gonna do those dishes. They stay in the sink because it's indeterminate. It's not quite clear who's taking up the dishes. So if you have two loads, how much that load carry this force and how much this load carry that force depends on what happens in between. Who does the dishes? The one with the least resistance, probably, to bugs infestation. So when you have 2 volts and the situation is statically indeterminate, how much load each support takes depends on things in between. So in order to do this, you cannot just use equilibrium. You also need the constitutive response, that is the material properties of your bar. Say, for instance, that this part of the bar was made of steel, and this part of the bar was made of strawberry jello, right? When I apply this force, I can tell you that the strawberry jello is not going to do much to carry that force. The steel is probably going to do a lot. So probably this side, which is attached to the steel, is going to feel a lot more reactions than this guy, which is only attached to the bar with jello, right? So the materials are going to play a role. And of course, the geometry, so compatibility, which has to do with geometry, is going to be, so both of these are needed to solve this problem, okay? Now, there are different ways to solve these statically indeterminate problems. And one way is called the displacement methods, and we're going to discuss that a little bit on Thursday on a slightly different kind of problems. But for this kind of problems, the method that's easier to use is called the force method. So we're going to use this force method for statically indeterminate problems. And the nice thing of this method is that it consists of 4 easy steps, kind of like a recipe, right? So you take these 4 easy steps, and you solve your statically indeterminate problem. So the first step, so step number 1, is to recognize that the whole crux of the problem is that you have 1 additional support. You would know how to do this thing if there was only 1 wall. You'd be happy with it. So what do? Well, you know what? I'm going to get rid of this extra support. So you remove your redundant support, and you substituted the unknown redundant reaction. So you look at this and you say, you know what, I'm going to take this whole extra wall away because I know how to solve this problem without the wall. I don't need the help, thank you very much. But because you remove the wall, you're going to just remove it and pretend it wasn't there. You have to recognize that this wall was doing something to this bar. It was applying some force. It was applying its unknown redundant reaction, Rxc. Now, which wall you take away, it's up to you. If you take away this, then this is your redundant reaction, and that's the wall that you took away. You could have done the opposite way. There is no particular reason of which one is better. And notice that when I drew Rxc, I drew it that way. And you should have been yelling at me and say, why did you draw that way? You didn't tell me which way X goes. Okay, so if I drew it that way, it's because in my mind, X was going that way. But in my mind, it doesn't work. You have to draw it. Okay, so I remove the redundant support. I substitute with the redundant reaction Rxc. And now this is a statically determinate problem. So this is the companion statically determinate problem. Guess what? You know how to solve this. So the second step, step 2, solve it. The statically determinate problem. And when I say solve it, I want you to obtain UXC. So solve it means obtain the displacement at the redundant support which is UXC in terms of your redundant reaction, right? You're going to find an equation for UXC, and RXC is going to be in it. So let's obtain it. So if the first thing that I do, I need to find N of X. And I'm not even going to plot the forces because, I mean, there is only one force. So when I find N of X, I'm going to do two things. I'm going to cut it for X greater than L, and I'm going to cut it for X less than L. If I cut here, the only C that I think is RXC and N of X. If I cut here, I see RXC, I see FD, and of course, where I cut, I have N of X, right? So this is me cutting the bar for the statically determinate problem to determine N of X. And I see because the situation here is different from the situation here, my equation for N of X is going to be split. It's going to be equal to simply RXC for L less than X less than L over 2, and it's going to be equal to RXC plus FD for 0 less than X less than L. Okay, I can do that. So my NX, if I want to plot it, it's going to look like that. So up here is going to simply be RXC. I go up by RXC. And up here is going to be RXC plus FD. Excellent. So from N of X.
Should that be 2L instead of L over 2?
Oh, yeah, sorry. Did I say L over 2? Oh, yeah. What was I thinking? Thank you so much. Okay? I'm one step ahead always and one step behind. Okay? We good? All right. Thank you so much, guys. Okay. So once I have N of X, I can figure out my strain. So I can just figure out then, if I get N of X, I can get my strain as a function of X. And my strain as a function of X is going to be N of X divided by EA effective of X. So actually, if I want to be careful, I would have to first do EA of X. And EA of X also looks like that. It's going to be EA0 on this side. And it's going to be 2 EA0 for the other half, right? So my epsilon of X, so let's do things in order. Like I told you, EA of X is equal to that. And so now if I do epsilon A of X, that's going to be equal to RXC divided by EA0 on the right side. So if L is less than X, is less than 2L. And it's going to be equal to RXC plus FD divided by 2 EA0 for 0 less than X less than L. Excellent. So my epsilon A of X also looks like that. And finally, from the strain, I can get my U of 2L, which is the U that, according to this loading, I'm going to get here. So this is UXC, how much that spot is going to deform. It's going to displace, sorry. UXC is displacement. So let me give myself a little more room. So UXC is U at 2L is going to be equal to U at 0, which is 0 because I have the wall. I'm solving this statically determinate problem. U is going to be 0 at the wall plus the integral from 0 to L of this guy of RXC divided by EA0 in the x plus the integral of this guy from L to 2L. And that is RXC plus FD divided by 2. Oh, this is 2EA0 divided by EA0 in the x. So this is how much the left side elongates. And I screwed up everything. So this goes from 0 to from L to 2L. This goes from 0 to L. And this is 2. I'm sorry. So how much the thing displaces is the integration of strain from the beginning of the bar to the end of the bar. This is made of two parts. You have to integrate epsilon A of x from 0 to L. And from 0 to L, you have this guy. And you have to integrate this thing here from L to 2L. And so when you calculate that thing, you're simply going to have L divided by 2E A0 that multiplies 2 RXC plus RXC plus FD. So this thing is the solution. This thing is the solution to your statically determinate problem. And you see that in your statically determinate problem, how much UXC will displace has to do with how big RXC is. Right? You're not getting rid of the whole mass yet, but you're very close to getting rid of the whole mass. Because what can you do now? What can you say? What do you do now? What do we know in the real problem? Any ideas? What do we know about the real problem? What is at C? A wall. What happens at the wall? Can the bar walk into the wall? Bingo. So what can we say? How much is UXC? 0. Zilch. And that's your your third step. So you solve your problem, and you found UXC in terms of RXC. Now you're going to impose your compatibility. Now you impose, and we are done. 4, impose compatibility. So you say that UXC must be equal to 0.
What was step 3 was? Is it step 3 or step 4?
Oh, step 3. I can count. UXC must be equal to 0. Right? So that means that 3RXC plus FD must be equal to 0. So that means that 3RXC plus FD must be equal to 0. And out of this constraint, you get that RXC is equal to minus FD over 3. You are done, my friends. And we can go home. Because now, what you need to do, you already solved the whole problem. See, you already have your solution. Now you know how much it is RXC. It's minus FD over 3. The fourth thing is you sub back, and we're not going to do it because we are out of time. But the fourth step is we sub back, and you get the solution to your statically indeterminate problem. Okay, so this thing here, we already have worked through everything, so we know how much epsilon A of x is. That would be minus FD over 3 EA. That one would be, minus, would be 2/3 FD over 2 EA, right? That's your strain. You integrate the strain over the length of the bar, you get your displacement field, and you find UXC at L. Okay? UX at L. All right? So we're going to do more of this. We're going to do problems on this, but this is the basic problem. So I'm going to post the solutions, which is going to have a little more. I will post my notes with a little more detail on this last part, and I will post an entire problem, a little more complicated than this. But the basic idea is you follow the step, you solve the statically determinate problem like you know, back substitute, and you're done. And I'm sorry about running late. Okay, thank you guys.